Tonight, we're going to explore one of the most catastrophic scenarios our planet could ever face. A single year in which the moon stops circling Earth and starts falling toward it. And it does not end the way you think it will. Long before the moon gets here, the ocean rises as high as a 10-story building, twice a day, every day. Every big city built next to the sea goes underwater and stays there. Then, the ground starts to shake. The moon pulls hard enough to crack solid rock, and volcanoes wake up all over the world. Nothing we have ever built can stop it. Not a rocket, not a laser, not every space program in history put together. And then, the moon never even lands. Earth pulls on it so hard that it breaks apart in the sky, and the broken pieces spread out into a ring around us. That ring wipes out every satellite we own, and it blocks the only way off this planet. By the end of tonight, we'll walk you through every stage of what you would face as the moon gets closer and closer to Earth. But before we get started, take a second to like and subscribe. If you enjoy these videos, it really helps a lot. Now let's begin. 365 days remain. For 4.5 billion years, the moon has kept the same arrangement with Earth. Never much closer, never much further, never once in any real doubt. Today is the first day that is no longer true. Picture the sky tonight. The same moon hangs where it always hangs. Calm, familiar, whatever sliver or full disk the calendar happens to show. Nothing about its appearance from the ground will change today, or tomorrow, or for weeks after that. But the numbers behind it already have. At this point in the countdown, T365, the two worlds sit exactly as far apart as they always have, 384,400 kilometers, the same figure people have used to describe the moon for centuries. That number is an average. The moon's path bends it a little closer and then a little farther, down to about 363,000 kilometers at its nearest approach, and out to roughly 405,000 kilometers at its farthest. A swing mathematicians measure with an eccentricity of just 0.0549. Translate that into plain terms, and it means the orbit is close to a perfect circle. Not the lopsided egg most people picture when they hear the word orbit. A number like 384,400 kilometers is easy to say and almost impossible to feel, so put something inside it. Line up the rest of the solar system. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Every other planet orbiting the sun, laid edge to edge like beads on a string, would just fit across the gap between Earth and the moon, with room left over at the moon's farthest point. That same distance is close to 10 times Earth's own circumference, roughly 10 trips around the entire planet, stretched into a straight line and thrown into the dark. Held up against the night sky, the moon looks no bigger than a coin at arm's length. The true scale hiding behind that small disk is what makes this whole scenario worth walking through slowly, one closing tear at a time, rather than skipping straight to the ending. A gap that size should feel like a guarantee of safety. For now, it almost does. The very first sign that anything has changed is not visible from orbit or through a telescope. It shows up on a beach, in a wave that climbs a few centimeters higher up the sand than it should. The moon's gravity reaching across the entire 250,000 kilometers and taking hold of the largest thing on Earth it can move, the ocean. Nobody panics over a slightly higher tide, but the object pulling that water has already turned toward Earth, and unlike every other night for 4.5 billion years, it is not turning back. This is the first of 5 stages the countdown will move through this year, and by a wide margin, the gentlest one. 4 harder stages are still ahead. Before going further, a smaller question is worth answering. The one children ask, long before anyone explains orbital mechanics to them. Why does the moon stay up there at all? It is moving sideways along its path at 1.022 kilometers per second, about 3,680 kilometers an hour, close to 4 times the cruising speed of a passenger jet. If that sideways motion ever stopped, Earth's gravity would pull the moon straight down. It never stops. And that is the entire trick behind an orbit. The moon's sideways speed carries it forward past Earth, exactly as fast as gravity pulls it inward. It is always falling. It is always missing. It never lands. It only circles. Imagine a cannonball fired so hard that the ground curves away beneath it as quickly as it drops, so it sails on forever instead of hitting the dirt. That is the moon. And until recently, that is all it had ever done. For 4.5 billion years, that same tug of war between falling and moving sideways has held quietly without incident, tracked and measured and predicted years in advance. The same trick keeps every satellite orbiting Earth right now, and every planet orbiting the Sun, fall and miss and fall again. It is not a metaphor. It is the entire mechanism holding the solar system together, and the moon is simply the closest, clearest example of it. The reason Earth can hold something moving that fast on a leash comes down to weight. Shrink Earth down to the size of a basketball, and the moon becomes a tennis ball drifting nearby, about a quarter of its width. The real numbers back up that picture. The moon's mass is about 7.35 times 10 to the 22nd kilograms, only 1/81st of Earth's own mass, and its diameter of 3,474 kilometers is close to a quarter of Earth's. Earth outweighs its companion by enough margin that even a fast, quarter-sized world cannot simply wander off. It falls around us instead of away from us, which is exactly what makes this whole scenario possible. If the moon were ever stripped of that sideways motion, dropped from right where it sits now and left to fall straight down under Earth's pull alone, how long would the crossing take? Not a slow drift. A 4.8-day fall. Not a distant threat either. Less time than a single work week is all it would take for the moon to cross the entire 250,000-kilometer gap and reach the ground. That single number is the whole reason this countdown exists. The real fall would be over almost before anyone could react to it, let alone prepare for it, let alone try to stop it. A 5-day collapse compressed into hours would give no time to understand any of it. So, the year stretching ahead is not a measurement of how fast the moon is actually moving. It is a choice, a deliberate stretch of that 5-day fall into 365 days. So each stage of what a closing moon would do to Earth, the tides, the tilted seasons, the shaking ground, the point where the moon itself gives way, can be examined in turn. And so the same question can be asked honestly at every tier along the way. Could anything still stop it? One more thing is worth carrying out of this opening distance, because it will matter more than a few extra centimeters of tide on a beach. The moon overhead has never been just a light in the night sky. For as long as it has been up there, it has quietly held two jobs. One steadies the tilt of this planet, and with it, the seasons every living thing on Earth depends on. The other governs the tides themselves, the same tides already beginning to climb. It has been catching itself here for 4.5 billion years, forever falling and never landing. It has been leaning against Earth's tilt the whole time, forever nudging the axis back towards stillness. It has been pulling at the sea the whole time too, forever dragging the water up the sand and back down again. Both of those quiet jobs depend on the moon staying roughly where it has always been. At T365, for the first time in its history, it no longer is. Before the first wave rises any higher, it is worth asking what the moon is quietly doing for us up there. Starting with something you would never connect to a rock in the sky. The seasons. The usual story about a closer moon is a simple one. Trade our mild seasons for extremes, deserts turning to ice, northern forests turning to furnace. It sounds dramatic. It is rarely explained. The claim gets repeated. The mechanism behind it does not. Picture a specific desert turned to ice and a specific northern country turned to furnace, and the image lands. But it is dramatization, not measurement. A colourful shorthand standing in for a physical process nobody bothers to walk through. Strip the specific places away, and what is left underneath is worth understanding on its own terms. And the real mechanism has nothing to do with heat radiating off the moon itself. It has everything to do with the tilt of Earth's own axis, the angle this planet leans as it circles the sun. That tilt currently sits at about 23.4 degrees. Left alone, it does not hold perfectly still. It breathes, drifting between roughly 22.1 and 24.5 degrees over a cycle that takes about 41,000 years to complete. A narrow, gentle sway, barely more than 2 degrees end to end. That narrow sway is the entire reason the seasons arrive on schedule, moderate and dependable, winter after winter, summer after summer, for as long as anyone has kept records. Here is the part that connects a quarter-sized ball of rock to something as large as climate. Earth's equator bulges slightly outward, a thickening around the middle produced by the planet's own spin, and the moon's gravity never stops pulling on that bulge. That steady pull forces the whole planet to wobble slowly, tracing a wide, lazy circle the way a spinning top traces a loop as it starts to lean. One full circle of that wobble, called precession, takes roughly 26,000 years to complete. Think of Earth as a spinning shaft, and the moon as a weighted wheel mounted on it. A wheel whose steady pull is what keeps the shaft from toppling. A fast spinning top stays upright through exactly this kind of wobble. Slow that same top down and it starts to stagger, leaning further with every rotation until it finally goes over. The moon's pull is what keeps Earth's version of that spin fast enough to resist a far worse kind of wobble, a resonance with the slow drift of Earth's own orbit around the sun. Resonance is the danger word here. Left to fall into it, that resonance is what would drag the axis into genuine, open-ended chaos. So what happens if that pull is taken away? In 1993, astronomers Jacques Lascar and Philippe Robutel ran the numbers for a moonless Earth, and the answer was not gentle. Freed from the moon's stabilizing tug, the axis would not simply drift a little further than usual. It could tumble, wander chaotically from nearly no tilt at all to past 85 degrees, a planet swinging so far over that it would periodically lie almost on its side, poles pointed nearly straight at the sun. That number held for years as the accepted picture. But here's where it gets strange. Later work complicated it rather than confirming it. A full simulation run in 2012 by Jack Lissauer, Rory Barnes, and John Chambers found a moonless Earth might typically wander only about plus or minus 10 degrees, nowhere near the full swing the 1993 mathematics allowed. Then, in 2014, researchers Wu Li and Konstantin Batygin sat down to reconcile the two, and found both were right in their own way. The extreme tilts are real and reachable, they concluded, but reaching them takes something on the order of 2 billion years. This is not a settled figure. It is a live scientific question, one still being argued over, and it is worth holding it as one rather than pretending to a certainty nobody actually has. There is a real planet next door that shows this is not just abstract mathematics. Mars has no large moon, only 2 small captured rocks, Phobos and Deimos, far too light to steady anything the size of a planet, and Mars's tilt genuinely is chaotic, swinging across roughly 0 to 60 degrees over long stretches of geological time, presently oscillating about 22 degrees around a 25-degree mean on a cycle of 125,000 years. Set that beside Earth's gentle 1.3 degree breathing, barely a flicker by comparison. Mars is not a projection or a model run on a computer somewhere. Mars is what an unguarded axis actually looks like, sitting there in the night sky as evidence, its seasons swinging wide and unpredictable across ages while hours hold steady. It is worth pausing on why that difference matters so much for a planet meant to carry life. A moderate, predictable tilt means predictable growing seasons, predictable migration windows, predictable ice ages that arrive and retreat on a rhythm slow enough for ecosystems to track. A tilt swinging across tens of degrees on short geological timescales offers none of that. Whatever adapted to one extreme would face a different planet a few 100,000 years later. Mars is a museum of what that instability does to a world. Earth, so far, is not. Now to what tilt actually does. Because this is where the science earns its payoff. The angle of that tilt sets how directly sunlight strikes each hemisphere, and how many hours of daylight it receives across a year, which is why one half of the planet runs warm while the other runs cold, the pattern reversing every half orbit. Under today's 23.4 degrees, Earth's equator receives about 2.4 times more sunlight annually than the poles do, roughly 415 watts of energy per square meter at the equator against about 170 at the poles. That ratio is the quiet reason the tropics stay hot and the poles stay cold, year in and year out. That ratio feels permanent, like a fixed law of how planets work. It is not. It is simply what our specific tilt happens to produce. Push the tilt past about 54 degrees, and the entire pattern flips over. The poles begin receiving more annual sunlight than the equator does. Not a small shift, a full reversal. Push the tilt further to an extreme 90 degrees, and the poles would draw in about 512 watts per square meter, while the equator dropped to just 205, less than half as much. The entire seasonal map turned inside out. This is the real content hiding behind talk of deserts freezing and northern country turning to furnace. Not one specific place gone hot or cold. The entire relationship between latitude and sunlight. The rule that has always decided which parts of Earth run warm and which run cold. Quietly capable of running backward. The moon looks passive from down here. A light for the dark and a tug on the tides. It is not passive. It is functioning as a gyroscope for an entire planet, holding a spin steady enough that the resonance which would otherwise wreck it never gets the chance to take hold. Without that pull, Earth's tilt could eventually reach the point where the poles draw in more sunlight than the equator ever does. That is the first of the moon's two hidden jobs, steadying the axis so the seasons keep arriving where everything alive on this planet expects them. The tilt is only half of what the moon holds in balance. The other half is the sea. At T300, the sea is the first thing to turn on us. 4 harder stages of the countdown still lay ahead, when the first of them stopped being gentle. The moon has closed from its ordinary distance of 384,400 kilometers down to about 250,000 kilometers, roughly 2/3 of the gap it used to keep. Tides now climb as high as 5 meters, and the first coastal cities begin to go under. New York, Miami, London. Buildings collapse under water they were never built to hold. Streets that have never flooded in living memory fill and stay filled. Foundations built for an ordinary sea now sit in one that no longer is. Residents move inland because there is nowhere else left to go. This is not the disaster. This is only its opening line. Wildlife goes first. Quietly, the way it always does. Sea turtles and pelicans are pushed off nesting beaches that no longer exist above the waterline. Generations of the same shoreline habits, suddenly homeless. And a second danger moves in underneath the first, slower, but just as real. Salt water is denser than fresh water, so as the sea pushes over coastal ground, it slides inland beneath the lighter freshwater layer, working its way toward wells and aquifers that never used to taste of salt. Drinking supplies begin turning brackish. Nobody drowns from that one. It just makes the water undrinkable, one well at a time, long after the tide itself has pulled back. So why does a closer moon do any of this? Why does distance alone turn an ordinary tide into a flood? Start with gravity itself. It falls off with the square of distance. Move the moon twice as far away and its pull is 4 times weaker, simple enough, and that alone would be an easy law to picture. But a tide is not built from gravity's raw pull on Earth as a whole. A tide is built from the difference in that pull between the side of the planet facing the moon and the side facing away, the small mismatch stretched across Earth's own width. Taking that difference, rather than the pull itself, adds one more power of distance to the equation. Tidal force does not fall off with the square of distance. It falls off with the cube. Picture the 2 sides of Earth for a moment. The side turned toward the moon, and the side turned away. The near side feels a slightly stronger pull than the planet's center does. The far side feels a slightly weaker one. Neither difference amounts to much by itself, but it is that gap between the two, the stretch, not the raw pull, that drags the ocean into a bulge. Shrink the distance to the moon, and that gap does not just grow, it grows compounded. Once for the ordinary weakening of gravity, and again for how much sharper the near-far difference becomes at close range. Halve the distance to the moon and tidal force does not double. It multiplies by 8. Double the distance and force drops by that same factor of 8. In reverse. Distance, not mass, wins the tidal tug-of-war every time. Think of it the way a lamp brightens far faster when you halve the distance to it than when you double its wattage. Closeness does the heavy lifting that weight cannot match. Here is the proof that this is a real law, not a convenient rule invented for a fictional moon. The sun outweighs the moon by about 27 million times. On mass alone, the sun should dominate the tides completely, and for most of physics, mass wins these contests outright. But the sun sits roughly 390 to 400 times farther from Earth than the moon does, and distance gets cubed, not just multiplied. Cube 390 and the number lands somewhere around 59 million. Cube 400 and it climbs past 64 million. Either way, that distance penalty is now larger than the sun's 27 million times mass advantage. Not mass, distance. The moon's tides end up about twice as strong as the sun's, despite losing the weight class by a margin of 27 million to 1. Run that same math on the countdown's own checkpoints. Divide 308 by 400 by 250,000, and the answer is close to 1.54. Cube that number, and it lands near 3.c, so at 250,000 kilometers, tidal force works out to about 3.6 times today's strength. Push the distance down to 100,000 kilometers, a stage this story reaches later, and divide 384,400 by that instead. The answer is close to 3.8. Cube it and the number climbs past 56, close enough to call it 57 times today's strength. Numbers like that look like a clean formula. Feed in a distance, read off a flood height. For a disaster written on paper, it would be tempting to stop right there. That is where the tidy formula runs out of road. The cube law describes force. It does not describe how many meters of water actually pile up on a given shoreline. Tide height is the ocean's own response to that force, shaped by the depth and geometry of every basin and coastline it crosses. And that response is not uniform from one coast to the next. The open ocean today sees only about 0.6 meters of tidal range under the moon's ordinary pull. Some coastlines, under that exact same moon, see over 12 meters. Same moon, same day. A 20-fold difference, purely from the shape of the coast that receives it. A shallow, narrow, funnel-shaped bay sloshes the way a full basin sloshes when you push it at just the right rhythm, the water piling higher and higher with each surge instead of spreading out and settling. A wide, open coastline barely notices the same push at all. The Bay of Fundy already climbs past 14 meters today, without the moon moving an inch closer. Wait, a coastline right now, under the moon's ordinary, undisturbed pull, outfloods the entire 250,000 kilometer tier this section just described. Some coasts do not need the moon to move at all to show what a closer moon would look like. They are already doing the impression every single day on schedule. So take the naive multiplier for what it is, a plausibility check, not a proof. At 250,000 kilometers, 5 meters is a reasonable estimate, well within what the shape of most coastlines could plausibly produce. Push the moon in further, toward the stages still ahead, and the honest answer only gets harder to pin down, not because the tides go quiet, but because no ocean on record has ever had to answer for a moon that close. No coastline has ever been measured against it. The number becomes a guess dressed as a figure. The lesson underneath all of it is the same one the coastlines are already whispering. The tides do not simply obey a number. They obey a shape, the shape of every basin and coastline they move through, and that makes them stranger, and in places crueler, than a clean formula alone would ever suggest. A formula can tell you the force is climbing. Only the coastline decides what climbing water actually does when it arrives. Why the ocean rises the way it does on both sides of the planet at once was a question this section had not answered yet. That question has a simple beginning, even if the full answer does not stay simple for long. The moon's single biggest job on this planet was never the countdown. It is the tide it raises every day, and without it, there would be essentially no tides at all. Take the moon away entirely, and the ocean goes still, a planet with almost nothing left, pulling its water into rhythm. The daily rise and fall that shapes every coastline on Earth traces back to a single rock overhead, and it is worth understanding exactly how before the countdown asks what happens when that rock moves closer. Start with the side everyone already understands. The moon's gravity is strongest on the half of Earth facing it, because that half is simply closer, and gravity always favors closer. That pull drags the ocean into a bulge, pointing straight at the moon. Nothing strange about that. It is the same reason anything gets pulled toward anything else, only aimed at seawater instead of an apple. But here's where it gets strange. A second bulge rises on the exact opposite side of the planet, facing away from the moon entirely. Something out there seems to be pushing water outward, away from the moon's pull rather than toward it. And the source that raised the question never actually answered it. How does the far side of an ocean bulge outward, away from the very object supposedly causing all of this pulling? Most people reach for the same wrong explanation. Earth is spinning, so surely the far bulge is centrifugal force, water flung outward the way a spinning fair ride throws its riders against the outer wall. It is a tidy guess. It is also wrong. The far bulge is not spin. It is not centrifugal force at all. It is gravity. The very same gravity that built the near bulge, just weaker at greater distance. Earth's solid body sits, on average, closer to the moon than the far ocean does, so the planet itself gets pulled moonward slightly harder than that far water does. The water does not keep up. It gets left behind. The planet is tugged out from under its own far ocean, and the gap that opens up is the second bulge. Picture a rubber band pulled unevenly from both ends, one end tugged harder than the other. It does not bunch up on the strong side. It stretches, long and thin, along the whole line of pull. That is what happens to Earth's oceans. They do not pile up on the moon's side alone. They stretch into a long, elongated shape, a bulge at each end, something closer to a football than a ball, with the seas between the two ends pulled thinner to feed them. There is a plainer version of the same idea, one anyone who has ridden in a car understands without ever thinking about gravity. Brake hard, and the people in the back seat lurch forward, not because anything pushed them, but because their bodies kept moving while the car slowed beneath them. The far ocean does something close to the reverse of that. The solid planet gets tugged forward, toward the moon, while the far water lags. It is left behind the same way a passenger is left leaning into motion. The car has already stopped making. Not centrifugal force, not the spin of the planet, gravity, weaker at distance, and an ocean simply left behind. That double bulge explains something else too. Something anyone who has stood on a beach has already noticed without knowing why. Earth spins once a day, turning underneath both bulges and the two shallower stretches of water between them. So most coastlines get 2 high tides and 2 low tides in a single day, not one. The day the tides run on is not quite the ordinary day either. It runs 24 hours and 50 minutes, not 24, because the moon keeps sliding along its own orbit in the same direction Earth spins, and Earth needs those extra 50 minutes just to catch back up to where the moon has moved to. High tides land about 12 hours and 25 minutes apart, half of that lunar day, and the far bulge usually comes in a touch smaller than the near one, which is why one of the 2 daily highs almost always runs a little higher than the other. The sun raises tides too, though it plays a supporting role rather than the lead. Despite its overwhelming mass, its distance leaves it pulling at only about 46% of the moon's strength, a little less than half. It cannot outmuscle the moon on its own, but it can lean into the moon's pull or lean away from it. And that leaning is what gives the tides their monthly rhythm. When the sun, Earth, and moon line up in a straight row, at full moon and at new moon, their pulls stack together and the tides swing to their highest and lowest extremes. The spring tides, nothing to do with the season, despite the name. When the moon sits at a right angle to the sun instead, around the quarter moons, the 2 pulls partly cancel each other out, and the tides flatten into their mildest version, the neap tides. Same moon, same sun, same ocean. The only thing that changes is the angle between them, and coastlines feel that shifting angle every 2 weeks, whether anyone on the beach notices it or not. None of this is new. It is the rhythm this planet has kept for longer than there have been eyes to watch it. The same 2 bulges, the same lunar day, the same monthly stretch between spring and neap, running on quietly for longer than there has been anyone standing on a shore to time it. And the rock record holds a strange footnote to that rhythm, laid down long before anyone was counting tides at all. Ancient tidal deposits, layers of sand and mud that only form where the sea rises and falls each day, preserve the rhythm the way tree rings preserve a season, one thin layer at a time. Read enough of those layers and they show that tides were once dramatically higher than they are now. Not a small difference. A different ocean entirely, climbing and retreating by a far greater range than any coastline sees today. The rocks do not explain why on their own. They only record that it happened. But the answer sits in the same relationship this whole scenario has been built around from its opening line. A closer moon means a stronger pull. A stronger pull means bigger tides. And the rock record is quietly describing a moon that once sat much nearer to Earth than it does now. Something in the deep past put the moon closer than it has ever been in living memory. Close enough to leave its signature in stone that still turns up underfoot today. Where that nearer moon came from, and why it does not sit that close today, was still an open question the ocean's own memory had just raised. Go back far enough, and the rocks are not describing a closer moon at all. They are describing the day the moon was made. Has anything like this scenario, a moon on a genuine collision course with Earth, ever actually happened before? And if the two worlds are as connected as the tides keep proving, how do we even know that connection runs all the way back to the beginning? The answer sits about 4.5 billion years in the past, nearer to the birth of the solar system itself than to anything written down in human history. A body roughly the size of Mars, about half Earth's diameter and carrying close to 1/10 of Earth's mass, struck the young, still-forming Earth. Scientists named it Theia, after the Titan who, in Greek myth, mothered the moon goddess. The debris thrown loose by that strike became the moon, not a passing visitor, not a captured rock, wandering close and getting caught, the way Mars picked up its 2 small moons. A piece of Earth's own violent birth, still circling overhead every night since. Start with when. The collision landed somewhere between 20 and 100 million years after the solar system began forming, close enough to the beginning that Earth itself was barely finished, still gathering the last of its own mass from the debris left over after the sun ignited. How Theia's path ever crossed Earth's at all is still a model, not an observed fact. One version places it at a Lagrange point, a gravitationally stable parking spot roughly 60 degrees ahead of or behind Earth on its own orbit. The kind of gravitational balance point where a smaller body can sit for a long stretch without drifting, held there for a time until the pull of Jupiter and Venus worked it loose and sent it drifting onto a collision path. Nobody knows exactly why that spot stopped holding it. No trace of Theia's orbit survived the impact that followed it. The strike itself did not come head-on. It landed oblique, at roughly a 45-degree angle, and it landed fast, faster than 9 kilometers every second, well past 30,000 kilometers an hour, several times quicker than a rifle bullet leaving the barrel. Think of it less like a head-on car crash and more like a sideswipe on the highway. A glancing hit that spins debris off the point of contact, instead of crumpling both vehicles into one wreck. That glancing angle is the reason so much material ended up flung into orbit, instead of the two worlds simply fusing into one. A head-on strike merges two bodies into one. A sideswipe scatters a second world into being. What happened to that scattered debris is where the story splits into two competing timelines. The older picture, the disk model, has roughly a fifth of Theia's mass, settling into a ring circling the young Earth, hot rubble slowly gathering itself into a single body. Half of that ring eventually pulled together into the moon, a process stretched out anywhere from under a month to a full century by the classic accounting. The picture did not hold. A high-resolution 2022 simulation from NASA and Durham University proposes something far faster. Not a century. Not even a month. Hours. In this newer picture, the moon was launched nearly whole into orbit in a single violent afternoon, assembled almost as fast as the impact that made it. The result is influential, not yet unanimous, but it also explains three things the slow model has always struggled with: the moon's tilted orbit, its unusually thin crust, and its strikingly Earth-like chemistry. That chemistry is the real backbone of the whole case, and it never rested on one clue alone. First, the Earth-Moon system carries an unusually high angular momentum, more spin and orbital motion than a quiet, undisturbed system should ever pick up on its own. Second, the moon shows every sign of having once been completely molten, a world-sized ball of liquid rock, cooling from the outside in. Third, its iron core is oddly small and its overall density oddly low, exactly what a body built from the surface debris rather than a fully formed planetary core should look like. Add its clear depletion in volatile elements, the substances that boil away easily under heat and should have survived in normal amounts on a normally formed world, an orbit that shares Earth's own tilt and orientation, and zinc isotopes that read as the signature of violent vaporization. And the case was already strong before a single moon rock had been weighed. Weighing the moon rock is exactly what closed it. For 50 years, the Apollo samples stood as the strongest proof available. Oxygen isotopes, the subtly different weights of oxygen atoms locked inside the rock, a kind of chemical fingerprint no two unrelated worlds should share, that matched Earth's own so closely the two worlds looked almost interchangeable, the kind of match that would satisfy a courtroom. Then, in 2020, a study led by Kano and colleagues found something unsettling. Deep-sourced lunar material carried a measurable difference after all. Not identical, close, but not the same, and close enough that doubt was suddenly back on the table after 50 settled years. The doubt held for 4 years. Then a 2024 study, led by Fisher and colleagues, measured 14 of the most pristine Apollo rocks ever recovered and pinned the real gap down precisely. Just 0.2 parts per million, give or take 1.6. A gap so small it is like weighing every grain of sand on a crowded public beach and finding, somewhere in all of it, a single grain sitting fractionally out of place. Within the precision of the instruments, Earth and Moon read as the same material. Not two worlds that merely resemble each other. One shared origin, confirmed once, doubted once, and confirmed again. How that near identity actually came to be, whether the two worlds truly mixed at the molecular level or simply happened to start from the same raw material, is still argued over. One idea, called a synestia, imagines the impact vaporizing so much rock that Earth's material and Thea's material swirl together into a single enormous, donut-shaped cloud of molten and gaseous stone before the moon ever condenses out of it, mixed so thoroughly that no clean seam remains between the two worlds. A newer challenger? Still only a 2025 preprint and nowhere near consensus, proposes the moon was never built from one impact at all, but from several smaller ones layering their debris together over time. Neither has won yet, and honest science is comfortable saying so. What is not argued over is that the moon never really stopped arriving. More than 700 confirmed lunar meteorites have turned up on Earth, 714 recognized as of December 2024 by one careful count, over 780 by another, many of them fragments of the very same fall, matched back together by researchers piece by piece. One such stone, weathered by decades buried in a West African desert, gets cut open to show an interior that has not seen daylight since it left the moon's surface, dark and unweathered inside its crust of desert wear. Hold a piece like that and the whole scenario compresses into something small enough to fit in a palm. The giant collision that built the moon 4.5 billion years ago never fully ended. It only slowed down from one Mars-sized strike to a scattering of stones small enough to hold in one hand, still falling, one quiet arrival at a time. The clock outside this story had not slowed down at all. The moon has always sent Earth small pieces of itself. At T200, it starts sending the ocean instead. 100,000 kilometers now separate the two worlds, the third of the countdown's checkpoints, and closer than anything the story has reached so far. The same cube law that turned a 250,000 kilometer gap into 5 meters of flood is now multiplying tidal force by nearly 60 times its ordinary strength. And the ocean answers in kind. Tides climb to about 30 meters, roughly the height of a 10-story building, arriving twice a day, everywhere a coastline exists, and receding twice a day only to come back. This is the tier where the map of the world actually shrinks. Not metaphorically. The coastline drawn on every atlas simply stops being where the water ends. Every waterside city becomes uninhabitable. Subways drown, roads drown, railways and highways vanish under water that never fully drains before the next tide arrives to add to it. What took a century to build can be unusable within a single lunar day. That phrase, infrastructure collapse, is easy to say and hard to picture. So picture something smaller first. Something that actually happened on a single ordinary day, with a fraction of this water. A single ordinary storm already showed what far less water can do. In 2012, Hurricane Sandy's surge reached only about 4 meters, a small fraction of what this tier demands, and it still flooded 9 of New York's 14 underwater subway tunnels. Switches corroded, signals failed, cables shorted under salt water that would not stop raising. The South Ferry station filled with roughly 80 feet of it, stairwell to ceiling. The system stayed dark for days, and the repair bill climbed past $4.5 billion. That was one storm, one surge, gone within a week. The water eventually pumped back out and the tunnels dried and relit. A permanent 30-meter tide does not go anywhere. There is no pumping out an ocean. Power fails the same way, at a larger scale. Hurricane Harvey's floodwater in 2017 damaged more than 90 electrical substations, 800 transmission structures, and 6,000 distribution poles, cutting power to more than 2 million customers at a peak loss of 11 gigawatts. A submerged substation cannot simply be dried out and switched back on. It has to be rebuilt from the ground up, a job that can take over a year and cost millions of dollars, one substation at a time, even when the flood that drowned it has already receded. Now picture every coastal substation on the planet submerged at once, permanently, with the water never receding long enough for a single repair crew to even reach the wreckage. No crew comes, no replacement part arrives. The grid simply stays dark, city after city, coastline after coastline. The failures do not stop at the waterline. Hospitals evacuate before the flood even reaches the front doors, because the machines keeping patients alive cannot run on a drowned grid, and a hospital without power is not a hospital anymore. It is a building full of people who need to be somewhere else immediately. Wastewater treatment plants lose power too, and without power they stop treating anything, dumping raw sewage straight into the rising water instead of processing it. What moves through a flooded city at this tier is no longer just seawater. It is seawater carrying everything a city was built to keep separate from itself, and it is carrying it into the same water people once swam in, fished from, and drew their homes around. Who is actually standing in this tier's path, and how many of them are there? The exposure is not a local problem. The low-elevation coastal zone, land sitting under 10 meters above sea level, covers only about 2% of Earth's surface, yet holds somewhere between 10 and 11% of the world's population, a share expected to climb toward 1 billion people by 2050. Nearly 2 out of every 3 cities with more than 5 million residents sit at least partly inside that zone. 13 of the world's 20 largest cities are coastal, built where they are for the same reasons ports have always chosen the water's edge: trade, fishing, easy arrival. A 30-meter tide does not strike a handful of unlucky towns. It strikes the address most of humanity already calls home. Even the water people cannot see is at risk. In 2013, Typhoon Haiyan storm surge poisoned a freshwater aquifer on Samar Island, so completely that officials estimated it could stay undrinkable for up to 10 years from a single storm. Hurricane Katrina and Hurricane Rita, arriving within weeks of each other, together buried freshwater wells across Louisiana under as much as 4.5 meters of salt water. Salt water is denser than fresh water, so it slides in underneath, seeping through the ground long after the visible flood has pulled back and the cameras have moved on. It does not need a flood to still be standing above ground. It only needs a flood to have happened once. At 30 meters, nothing pulls back, and nothing seeps back out again either. The drinking water goes the same way as the subways, quietly, and does not return. The coastline itself stops functioning as a coastline at all. Researchers modelling sea turtle nesting habitat project losses of 62% by the middle of this century and 87% by the year 2100 at one closely studied site, and that is under ordinary sea level projections. Decades of slow, gradual rise, not a countdown clock measured in months. Caribbean nesting beaches alone are projected to lose 26 to 32% of their area under just half a meter of rise. Half a meter. This tier brings 60 times that. Every dry strip of sand a nesting turtle depends on disappears with it, and disappears in a single season rather than a slow retreat across generations. A 30-meter tier does not thin out coastal nesting. It erases it. So which cities actually make it through this tier? Name the ones everyone assumes would still be standing. New York, Shanghai, Mumbai, their subways, their ports, their power grids, all built low and close to the water, the way great harbour cities have always been built, because the water was the reason they existed at all. All of it gone under this tier. Not those cities. The places that actually stay dry are the ones nobody has ever thought of as coastal at all. Denver sits at exactly 1,609 meters, a mile above sea level. Calgary sits near 1,045 meters. Mexico City sits inside a closed mountain basin at roughly 2,240 meters, sealed off from any ocean by geography alone. All three sit comfortably above even this tier's 30 meters, high and dry while the world's great harbors disappear beneath them. Altitude, a fact almost nobody has ever needed to know or care about, becomes the entire difference between drowned and dry. A number in a geography textbook turns into the line between a living city and a submerged one. But dry is not the same as safe. The ground beneath those refugees has not been tested yet, and it will not stay untested for long. It is about to be. Before that ground gets tested, the countdown is worth pausing for a moment, because everything it has shown so far runs in exactly the wrong direction. The real moon, the one actually hanging in the sky tonight, is not falling toward Earth. It never has been. It is moving away, drifting outward at about 3.8 centimeters a year, roughly the pace a fingernail grows. That is not a guess, and it is not a rough estimate rounded off for the sake of a tidy sentence. It is one of the most precisely measured numbers in all of astronomy, and the measurement itself is almost as strange as the fact it proves. In July of 1969, the astronauts of Apollo 11 left a panel of mirrors sitting on the lunar surface. 100 small corner cube reflectors set into a frame no wider than a kitchen tray, 46 centimeters across. Each of those mirrors is built to send a beam of light straight back toward wherever it came from, which is what makes catching a returning pulse across so vast a gap possible at all. Apollo 14 and Apollo 15 left more of their own. A French-built reflector rode a Soviet rover to the surface and left a fourth. Ever since, observatories on Earth have fired laser pulses at those mirrors and timed how long the light takes to make the round trip. The timing is accurate to about a millimeter, precise enough to measure the entire distance between Earth and the Moon, and be wrong by less than the width of a paperclip. Do that every year, for decades, and the tiny yearly drift stops being noise and starts being a trend line. That precision has pinned the recession rate down exactly, 3.830 centimeters a year, plus or minus 0.008. Not falling, climbing. The reason is the same physics already covered. The same two bulges that raise the tides twice a day, just working in reverse. Earth spins once every 24 hours, far faster than the moon completes an orbit, which takes 27.3 days. That mismatch drags the tidal bulge slightly ahead of the moon as Earth spins beneath it. The leading bulge then pulls the moon forward along its path, nudging its orbit wider, while the moon's own pull on that same bulge drags back on Earth's spin. Two effects, one cause, opposite ends of a single exchange. The same mechanism that could someday drown a coastline is, right now, quietly pushing the moon further from us instead of closer. It is the same near bulge and far bulge from earlier. The same football-shaped stretch of ocean, just doing its ordinary work under the moon we actually have rather than the one this story imagines. None of that motion disappears. It only changes hands. A figure skater who pulls their arms in spins faster. Extend the arms back out and the spin slows. The same total momentum spread across a wider circle. Earth and the moon are running a slower version of the same trade, over millions of years instead of a few seconds on ice. Earth's spin is losing momentum. The moon's orbit is gaining it. Nothing is created, and nothing is destroyed. It simply moves from one side of the relationship to the other. One ledger, always balanced. Here's where the numbers stop agreeing with each other. Models built from the modern recession rate predict Earth's day lengthening by about 2.3 to 2.4 milliseconds every century, a stretch smaller than the blink of an eye spread across 100 years. But the actual record, ancient eclipse timings stretching back 2,700 years, shows a slower rate, 1.72 milliseconds per century, plus or minus 0.03. The two figures do not match, and the likely reason is unglamorous. Parts of the ground are still rising, places like Canada and Scandinavia slowly lifting back up, now that the ice sheets that once crushed them under their weight are gone, moving at a pace of millimeters a year, but quietly working against the moon's braking the whole time. Scientists have not closed that gap yet. It stays open, an honest disagreement instead of a tidy number, and that is worth sitting with for a second. The tidal mechanism is not in doubt. Only the exact pace of its effect is, and a science that admits what it does not yet know is doing exactly what it should. The deep past confirms the direction, even where the rate stays uncertain. Layered tidal sediments called rhythmites, thin bands of mud and sand that recorded the rhythm of ancient tides, the way rings record a tree's age, put Earth's day at somewhere between 17 and 19 hours around 2.5 billion years ago. By 620 million years ago, it had stretched to about 21.9 hours. And somewhere in between, the record does something strange. Between roughly 2 billion and 1 billion years ago, the day length goes flat. Stuck near 19 hours for almost a billion years, a stretch geologists call the Proterozoic stall. The leading explanation is a kind of resonance. The sun's own pull on the atmosphere quietly speeding Earth's spin back up just enough to cancel the moon's braking, until the continents drifted into new positions and the balance broke. That is a hypothesis, a good one, backed by the shape of the data, but still a guess about a billion years nobody was alive to watch. Nobody has proven it yet. The clearest confirmation left standing is not a rock. It is a fossil. In 1963, a paleontologist named John Wells counted the daily growth rings in coral that had formed 385 million years ago, well over 100 million years before the first dinosaurs existed. Each coral had laid down a fine ridge for every day it lived, the way a tree lays down a ring for every year. Wells counted about 400 of them per year, not 365. Devonian days were shorter than ours by a couple of hours, and a Devonian year, the same length in absolute time, simply held more of them. Nobody needed a laser or a satellite to find that clue. It was sitting in the rock the whole time, waiting for someone to count it. A second, independent proof of the same drift the mirrors on the moon confirmed today. None of it runs forever. In roughly 1 to 1.5 billion years, somewhere between a fifth and a third of Earth's entire history so far, something else ends the whole exchange. Not because the moon reaches some final distance, because the ocean it depends on will be gone. The sun grows bright enough to boil Earth's oceans away, and with no water, there is no tidal bulge, no friction, and nothing left to trade. The mechanism that has moved momentum between Earth and the Moon for 4.5 billion years simply stops, long before it could ever reach the point where a day and a month become the same length. The real Moon drifts a little further. Then it drifts no further at all, holding at whatever distance it has reached when the oceans finally go. This is the second of the Moon's 2 hidden jobs, finishing its quiet work in the background, not steadying the axis this time, but stepping back instead of closing in. That is the truth running underneath this whole countdown, and it keeps running there, unseen, while the clock in this story counts down anyway. The next tire does not care what the real Moon is doing above it. It only cares about the one that is falling, and at 100,000 kilometers, that one is about to reach the ground itself. The ground itself does not stay a bystander for long. At T100, the Moon has closed to 100,000 kilometers, and the danger shifts from water to fire. Storms will not simply intensify. Whole weather systems destabilize, patterns that held steady for centuries breaking apart as the atmosphere answers a nearer Moon's pull. Hurricanes and violent storms multiplying across a planet that no longer has a fixed sky to organize itself around. But the deeper threat sits lower than any storm, down in the rock underfoot, and it is the one the countdown has not had to explain until now. The ground under our feet feels permanently solid, permanently still, not motionless, not quiet either. The Moon already flexes solid Earth, not only the oceans, and it has been doing this every single day since long before anyone was around to notice it. Twice a day, a body tide lifts the crust itself, somewhere between 20 and 55 centimeters depending on where you stand, about the distance from the floor to a doorknob. The land under a city rises and falls on a schedule as regular as the oceans, and almost nobody feels it happening. Rock stretches far less than water does, roughly a third as much, which is why the sea rises in meters today, and the ground only in centimeters. Same mechanism, working on both, every day of every year, quietly, at a scale too small to register as anything but stillness. Smaller motion, for now. Halve the distance to the Moon and tidal force multiplies by 8. That is the same law that turned an ordinary tide into the first flood 2 tiers ago, and it does not stop applying just because the target changed from water to stone. Run it again at 100,000 kilometers, and tidal stress on the crust and mantle climbs to roughly 57 times today's. Picture leaning one hand against a door, barely enough pressure to feel the hinge shift. Now picture the weight of a loaded truck pressed against that same door instead. That is the difference between the stress rock feels tonight and the stress it would feel at this range. The same force, the same law, simply run much closer. And rock does not bend the way water does when a force like that arrives. It cracks instead. The Moon itself is standing proof that the mechanism runs in both directions. Hundreds of miles beneath its surface, Earth's pull triggers deep moonquakes, what seismologists call a tidal event, the same stick-slip rupture that drives an earthquake here. Apollo seismometers recorded more than 12,000 of them, rising from 81 separate source regions scattered across the Moon's interior. The shallow ones reach magnitude 5.5 and keep ringing for over 10 minutes at a stretch. Because a dry, rigid Moon has nothing in it to damp the waves the way Earth's wetter, more fractured rock does. Earth quiets its tremors in seconds, water and soil and living crust absorbing the shock. The Moon rings like a struck bell, and keeps ringing, for minutes at a time, in near total silence, with no ocean and no weather to muffle it. On Earth today, that same pull already nudges earthquake timing, modestly but measurably. A Greek study found quakes about 15% more likely at the peak of the Sun's own tidal pull, a pull far weaker than the Moon's, and the effect shows up strongest exactly where the crust already carries strain, the mid-ocean ridges, and the volcanic belt where rock sits closest to its breaking point already. Chief among those belts, the Pacific Ring of Fire, a horseshoe of fault lines and volcanic chains nearly 40,000 kilometers long, close to the distance around the entire planet. It already holds about 75% of the world's active volcanoes, well over 450 of them, and it is the site of about 90% of the world's earthquakes. Plate tectonics built that ring over hundreds of millions of years, not tides. But a nearing moon would load faults that are already primed to fail, adding one more strain to a system that is already stretched close to its limit, tightening a fuse that was lit long before this story began. Could gravity alone actually wake something on that scale? The sharpest proof does not come from Earth at all. It comes from Jupiter. Jupiter's innermost large moon, Io, is caught in a permanent tug of war. It is held slightly off balance by an orbital resonance with two neighbouring moons, Europa and Ganymede, a gravitational rhythm that never lets Io settle into a stable, quiet orbit. That imbalance means Jupiter's tidal pull flexes the little moon's rock with every single orbit, and flexing generates friction, and friction generates heat, the same way bending a wire coat hanger back and forth over and over eventually leaves the bend too hot to touch. No impact struck Io. Nothing there is burning in the ordinary sense. It is gravity alone, working a solid world from the inside until parts of it liquefy, over and over, orbit after orbit, with no end in sight. The result is the most volcanically active body found anywhere in the solar system. Io carries more than 400 active volcanoes, as many as 300 of them erupting at the same moment, radiating something like 30 times Earth's own internal heat out into space. Its lava runs past 1800 Kelvin, past 1127 degrees Celsius, hot enough to melt steel outright and keep going. The hottest surface temperatures found anywhere among the planets and their moons, produced by nothing but a gravitational pull, tightened and loosened, over and over, forever, on a small moon that never touched anything to earn that heat. Not invented physics then. The same tidal flexing already tearing at a small moon of Jupiter right now, tonight, aimed for the length of this scenario at home instead. The honest limit belongs in the very same breath as that reveal. Tidal triggering of earthquakes has not been clearly demonstrated everywhere at once. The effect concentrates on faults already close to failure, and it stays statistically modest, regionally uneven, real but far from universal. No study models an actual inbound moon at 100,000 kilometers, setting the entire ring of fire ablaze at once. The Io comparison proves the mechanism is real. It does not forecast the exact scale, or the timing, or which fault gives way first. The 57 times stress figure is a valid calculation, worked out from the same inverse cube law behind every tide in this story, but it is not a peer-reviewed prediction of what erupts, where, or when. Honest science holds both of those at once, the mechanism proven and the outcome unmeasured, without pretending the gap between them does not exist. Still, the ground does not need a forecast to already be answering. It rises, it falls, it rings, hundreds of miles down, on a world with no ocean at all to blame for any of it. That was only the second of the countdown's harder stages. Water first, then stone. One tier still waited past this one, and it was the tier where nothing built by human hands, no engine, no rocket, no plan drawn on paper, would be enough to stop what was already coming. Nothing built by human hands would be enough, and that is a heavy claim to leave sitting in the dark without testing it first. Because humanity has actually tried something close to this, not against the moon, but against a much smaller target, with real hardware instead of a hopeful guess. On September 26, 2022, NASA aimed a spacecraft at a small moon called Dimorphos and let it hit. Dimorphos orbits a larger asteroid, Didymos, millions of kilometers from Earth, and neither one posed any actual threat to this planet. That was the point. It was a test target, chosen precisely because nothing was at stake if the attempt failed, a rehearsal for a danger that has not arrived yet. The mission itself was the first real test in history of what scientists call kinetic impact deflection, hitting an object hard enough, at the right angle, to physically shove it off its path rather than merely watching it. The spacecraft, roughly the size of a vending machine, massed somewhere between 570 and 580 kilograms. It struck Dimorphos at about 6.1 kilometers a second, more than 20 times the speed of sound, closing the last stretch of its approach faster than the eye could have tracked it. Telescopes on Earth had been watching Dimorphos's orbit for months before the impact, timing it against Didymos with enough precision to catch a change of minutes on a body millions of kilometers away, and they kept watching after. It worked. Not a little. Dimorphos's orbit around Didymos shortened by 33 minutes and 15 seconds. Momentum from the spacecraft alone should have bought roughly 7 minutes. The other 26 came from something the impact kicked loose. Plumes of rock and dust blasted off the surface on contact, what scientists call ejecta, and that flying debris carried away several times more momentum than the spacecraft itself delivered, an enhancement factor of about 3.6. A small, deliberate hit, amplified by the target's own body flying apart around it. Even that number carries a quiet asterisk. Whether the same boost would repeat against something as large and as tightly bound by its own gravity as the moon has never been tested, and likely never will be until it matters. Small rubble piles fling debris easily. A world that has already pulled itself into a sphere, held together by its own weight for 4.5 billion years, might not shed material the same way at all. So could the same approach turn the moon aside, push it back onto its old harmless orbit before it ever reaches Earth. Here is where the hope runs into a wall it cannot climb. Dimorphos is not a moon in any real sense. It is closer to a loose pile of rubble drifting in formation, somewhere between 160 and 177 meters across, about the footprint of a large stadium. Its entire mass comes to somewhere between 4.3 and 5 billion kilograms, close to the weight of the Great Pyramid of Giza. That is what one half-ton spacecraft, moving fast, was able to nudge. The moon masses 7.35 times 10 to the 22nd kilograms. Set the pyramid weight of Dimorphos beside that number, and the comparison stops behaving like a comparison. It is not close. It is not measured in multiples a person can picture. 10 trillion. The moon outweighs the very asteroid Dart already redirected by roughly 10 trillion times, about 13 orders of magnitude, a 1 followed by 13 zeros. Not a stadium of loose rock. 10 trillion Great Pyramids, fused into a single, gravitationally whole world that has never once needed to hold together against an outside push. Other ideas exist on paper, and neither one closes the gap. A gravity tractor, a spacecraft that simply parks nearby for years and tugs with nothing but its own faint pull, patient rather than forceful. A nuclear standoff burst, a fast, violent push meant for a large asteroid spotted too late for anything gentler. Both are studied seriously by real agencies planning for real, if unlikely, asteroid warnings. City-sized rocks discovered with only years or months of notice. Both were designed for rubble, roughly Dimorphos's size, tens of meters to a few kilometers across. Neither one comes close to scaling up to a body carrying 1/81st the mass of Earth itself, a target thousands of times wider and inconceivably heavier than anything either method was ever meant to touch. There is exactly one serious published estimate for actually moving the moon, and it exists mainly to prove the idea absurd. Mine the lunar surface, fire the material away with a laser rated at 100 gigawatts, about the combined output of every wind turbine spinning across the United States, and use the recoil to slowly push the moon into a new orbit. The estimate, roughly 300 trillion years. The universe itself is about 13.8 billion years old. Moving the moon this way would take more than 20,000 times longer than the universe has existed so far, and the moon would still be almost exactly where it started when the job finished. Try it with rockets instead, and the number does not improve. About 7 times 10 to the 16th Falcon Heavy launches, set against a real total of roughly 70,180 orbital launches across the entire history of spaceflight. Every rocket fired by every country, combined, from the first satellite to the newest crew capsule. Multiply that whole recorded history by more than 1 trillion, and it still falls short. No space agency treats moving the moon as an actual engineering problem. The only serious analysis of it exists to show why nobody should try. So the honest answer to the human question is short. No technology that exists, or that anyone can currently imagine, could move the moon by a distance worth measuring. If the moon were truly falling, nothing built on Earth would catch it, slow it, or turn it aside. Not a spacecraft, not a laser, not the combined output of every space program in history, stacked on top of each other. But that is not the same as saying nothing can stop the fall. It means the only thing capable of stopping it was never going to arrive as a rescue. It was always going to arrive as a destruction. The moon meeting a force it cannot survive. One that needs no engine, no launch, and no human decision at all to show up on schedule. It was already waiting, closer than anyone building rockets had been asked to look. It was already waiting, and at T0 it finally arrives. The moon has spent an entire compressed year as one intact world, cratered, aging, unmistakably whole. That ends here, not with a touch, not with a crash anyone could point to and call the moment of impact. The moon reaches about 18,000 kilometers from Earth, and Earth reaches back without ever laying a hand on it. This is the countdown's third and final stage, the one nothing built by human hands could have postponed. Everything since T365 has been leading here. The tides, the tilted seasons, the cracking crust, the failed rescue. None of it changed where this ends. This distance has a name. It is called the Roche limit, and it is the point where a body held together only by its own gravity stops being able to hold itself together at all. Every tide in this story has come from the same source, the difference in pull between the near side of a world and the far side, the stretching force that scales with the cube of distance, not the square. Halve the distance to a tide-raising body, and the force does not double. It multiplies by 8. At 250,000 kilometers, that's scaling flooded coastlines under 5 meters of ocean. At 100,000 kilometers, it cracked solid rock under nearly 60 times today's stress. At 18,000 kilometers, the same law, run to its extreme, finally does something new. The tidal force stops merely stretching the moon and starts outweighing it, overwhelming the moon's own gravity, the very grip holding its rock and dust together as a single sphere. Past this line, a moon does not survive intact. Nothing does. The number itself is not one clean figure. Treat the moon as a rigid sphere and the math gives a Roche limit of about 9,500 kilometers from Earth's center, tighter than the real breakup point. But the moon would not stay a rigid sphere as it approached. It would stretch first, pulled long into an ellipsoid before it ever came apart, and a body that flexes and deforms breaks earlier than one that stays stiff. Model it as fluid instead of solid, and the limit widens to somewhere between 18,150 and 18,400 kilometers, which is where the scenario's own 18,000 kilometer figure comes from. Other published estimates land higher still. One widely cited NASA-sourced figure puts it near 90,900 kilometers. The spread is not a disagreement about the physics. It comes from different assumptions about how dense and how rigid the moon really is. The mechanism tearing it apart is not in question. Only the exact address is. Here is the number worth sitting with. The real moon orbits at 384,400 kilometers. That is roughly 20 times farther out than the fluid Roche limit, and even at its closest approach, perigee, it never comes close to crossing it. For the moon to be in any real danger, it would need to fall to about 1/20th of the distance it actually keeps. That is exactly why everything in this scenario is fiction, and exactly why it takes a full invented year, a moon stripped of its sideways motion, to bring it anywhere near this line at all. Hold on to that number. It matters more than it seems to right now. But at T0, inside the fiction, the line is crossed. And what happens next is not the crash a listener has been quietly bracing for all year. Think about what has actually stayed constant since the opening minute of this countdown. A distant light in the sky, pitted with craters, unmoved in shape for 4.5 billion years, present in every photograph humans have ever taken of it. At T0, for the first time in that entire history, it stops being one thing. The moon does not slam into Earth as a single mass. It comes apart first. Tidal stretching pulls the near side harder than the far side. The same asymmetry that once raised 2 ocean bulges instead of 1, only now strong enough to shear the whole body rather than merely lift water off it. Cracks widen into fractures. Fractures widen into gaps. The moon opens into a spread of fragments, dust grains at one end, asteroid-sized boulders at the other. And here is the part that runs against instinct. Those pieces do not fall back together. Inside the Roche limit, the same tidal force that tore the moon apart also stops the fragments from regathering into a new body. Outside the limit, loose material tends to clump under its own gravity. Inside it, that same gravity is overwhelmed again and again, and the debris spreads instead, thinning into a ring rather than reassembling into a smaller moon. This is not a hypothetical mechanism dressed up for one video. It has been photographed. In July 1992, the comet Shoemaker-Levy 9 passed about 40,000 kilometers above Jupiter, inside Jupiter's own Roche limit. Nothing hit it. Jupiter's tidal pull alone was enough. The comet broke into 21 pieces, a line of fragments astronomers nicknamed the String of Pearls, strung out along its orbit like beads pulled off a snapped necklace. 2 years later, in 1994, those 21 pieces struck Jupiter one after another. But the breakup itself, the part that matters here, had already happened without a single collision. Gravity did it alone, from a distance, in the open dark between 2 worlds. Saturn carries the same proof, permanently, in plain sight. Its rings sit inside Saturn's own Roche limit, which is exactly why that debris has never gathered itself back into a moon. Every time loose material there tries to draw together, Saturn's tides pull it apart again, and the rings simply persist, locked in the same disintegrating equilibrium a shattered moon would enter around Earth. And the process is not finished elsewhere either. Mars's small moon Phobos is spiraling inward right now, drifting closer by about 1.8 meters every century, and it is expected to cross Mars's own Roche limit and shatter into a temporary ring of its own in roughly 30 to 50 million years. Saturn shows the aftermath. Shoemaker-Levy 9 showed the moment itself. Phobos is still on its way there, closing the distance a fingernail's width at a time. Between the 3 of them, every stage of this exact physics has already been observed somewhere in the solar system. None of it needed to be imagined. What is not settled is how a broken moon would behave in the minutes and years after breaking. Whether the debris spreads into something that holds, a genuine ring, or thins unevenly and starts raining down sooner, or falls more directly without ever really settling, depends on details this scenario cannot pin down precisely. The exact speed and spin the fragments carry at the moment they separate. The sources that model this kind of breakup describe several plausible outcomes rather than one certain path. That is not a gap in the story. It is an honest limit of the physics itself, the same kind of honest limit that showed up when the tilt simulations disagreed, and when the 2 day-lengthening rates would not quite match. So picture it landing here, at Earth, at T0, not a mountain of rock arriving in one violent instant. A widening band of fragments, torn loose without ever touching the ground, spreading into the same kind of ring that circles Saturn and once, briefly, circled Jupiter's shattered comet. Dust at one edge of the spread, boulders the size of buildings at the other, and between them, everything in between, all of it now orbiting rather than falling, at least for now. The ending this whole year has been building toward is not an impact at all. It is a birth. The birth of a ring, hanging directly over the same coastlines that flooded first, and the same fault lines that cracked under the tidal stress before it. That ring will not stay still, and it will not stay harmless. The moon does not end as a crater. It ends as a ring, and the first thing a ring does is fall. Picture what the whole year seemed to be building toward. One clean strike, a single mass arriving in a flash that levels a coastline and is finished by morning. That is not what happens at T0. Most of the shattered moon never touches the ground at all. It orbits, Dust at one edge of the spread, boulders the size of office towers at the other, and between them, a loose, chaotic band now circling Earth instead of falling toward it. The asteroid that ended the dinosaurs came from one direction and struck once, and then it was over. What now surrounds Earth arrived from every direction at once, and it has not finished arriving. It will not finish for a very long time. That is the real shape of this ending, and it is why the countdown's final stage did not close with the one loud, singular event most of the last year had quietly assumed was coming. It closed with something stranger. An entire small world, for now, turned into a slow blizzard with no edges. Because a ring this new is not tidy, and it is not safe. It rains. Meteor showers that used to flare for a single night, a few dozen streaks an hour, worth setting an alarm to watch, become permanent weather instead. Most of what is falling is dust, burning up harmlessly high in the thin blanket of air wrapped around the planet, a bright, constant sparking overhead where the sky used to sit still. Some of it is not dust. Asteroid-sized fragments, pulled down by Earth's own gravity and slowed just enough by the friction of passing through that same air, keep coming down not once, not for a season, but continuously, indifferent to which coastline or which crater field happens to be underneath. The precedent for how long that rain actually lasts sits in Earth's own deep past, and it runs far longer than anyone standing under this new sky would want to hear. That part of the story is still ahead. For now, only this much is certain. The sky does not clear. Not this week, not this year. What used to be an omen, a shooting star, a wish thrown at the dark, becomes instead the ordinary condition of the sky. Background noise nobody looks up for anymore. Overhead, something else fails first. Faster and just as total. Every satellite Earth has ever launched sits inside the same debris field, now sweeping around the planet. And a cloud of gravel moving at orbital speed does not need to aim to be lethal. Here is what breaks before the ground even finishes shaking. The whole fleet is destroyed. All of it. Gone in the opening hours, before the ring has even begun to settle into any real shape. GPS goes with it. The satellite network that quietly tells a phone, a ship, an airliner exactly where it stands, and every one of them goes blind at the same moment. Weather forecasting goes with it, so the next storm arrives with no warning at all, no 5 days of notice, no time to move anyone out of its path. The links that carry a phone call or a broadcast across an ocean go with it too, cut all at once, rather than one at a time. Earth does not lose its lights, it loses its nervous system, and it loses all of it in the same hours the first rocks start falling. Every ship that trusted a satellite to tell it where the reef was now has to trust a paper chart and a compass instead. The way sailors did for most of human history, only now with no forecast to warn them what is coming over the horizon. And here is the part that turns a bad night into something sealed shut. A ring sounds like it should be survivable, even distant. Something to watch from underground and simply wait out. Not a scar. Not a souvenir hanging politely overhead. A wall. Even a spacecraft that still works. Fuel tanks full. Engines fully ready. Cannot simply climb through it. Every path off the planet now runs straight through a band of rock, moving fast enough to shred a hull on contact. Thousands of fragments waiting in every direction a rocket could possibly point. There is no gap to thread and no window to wait for, because the band does not part, it only thickens. Humanity has just lost the moon. In the same hour, it loses the way out. The species that spent a century building rockets to leave is sealed to its own ground by the wreckage of the one world it always meant to visit first. 4 things have happened within the same handful of hours. The moon became a ring instead of a crater. The rain began. Every satellite died at once, and the way off the planet closed behind it. None of the 4 is temporary, and none of them waits for the others to finish before starting its own damage. What that wreckage looks like right now is not what it will look like later. In these first hours, it is scattered and shapeless, rock strung out unevenly all around Earth, chaotic, lethal, with no visible order to it at all. closer in places, thinner in others, nothing yet resembling a shape a person could draw. Only across a very long stretch of time would it settle and flatten, thinning toward Earth's equator into the kind of narrow, gleaming band that circles Saturn, the picture every photograph of that planet has already trained the eye to call beautiful. It would be, seen from far enough away, a bright thread laid across the sky at dusk. Underneath it, close, it is the opposite of beautiful. It is simply the thing now standing between Earth and everywhere else. How long that settling actually takes is not a small question, and it is not one this moment can answer. Whether it takes a human lifetime or many, whether the sky above any one place ever really goes quiet again, is left open here on purpose. Earth may already know the answer better than it seems. Something very much like this may have happened here before, and the sky still carries the evidence, if anyone knew where in the rock to look. The evidence sitting in that rock is not about falling stones. It is about a shadow. A ring does more than rain debris on the world underneath it. It blocks light, steadily, for as long as it hangs there. And losing that light does more damage over time than any flood or any quake managed on its own. The band would not shade Earth evenly. It would thin some daylight hours and erase others outright. A moving stripe of dust crossing the map on no fixed schedule, brighter under some skies, genuinely dark under others, depending only on where the debris happened to be thickest that day. Nobody dies from a dimmer noon on the first afternoon. That is exactly what makes this threat different from the ones already covered. It does not announce itself with a wave or a tremor. It works by subtraction, a little less light every day, for longer than anything alive on the surface can simply wait out, and that dimming would not stop at the ground. It reaches down to the base of everything alive. Plants feel it first. Slower growth, thinner harvests, whole growing seasons quietly shortened. But the deeper damage happens somewhere most people never think to picture. The open ocean, in the drifting, near-invisible life called phytoplankton. Phytoplankton produce something like 50 to 85% of the oxygen entering Earth's atmosphere, more than every forest on land combined. Something close to every second breath a person draws. Less light means less photosynthesis, in the crops on land and in that drifting ocean life alike. And cutting phytoplankton's light does not just dim a view. It reaches straight into the air itself, for whoever is still standing to breathe it. The population that survived the drowned coastlines, the shaking ground and the fire in the mountains is already smaller and already hungrier. A thinner oxygen supply does not need to reach zero to matter to people in that condition. No study has actually modeled a ring shadow choking off photosynthesis this precisely. This is the physics of light and oxygen, followed honestly to its likely conclusion, not a measured result, and it deserves to be held that carefully. The cold follows the dark. Shifting shadows sweep across different regions as a ring turns overhead, plunging whole stretches of the planet into deep, sunless cold for days or weeks at a stretch. And cooling on that scale would finish off whatever food supply survived the water and the fire already. Not a hard season. A slow, planet-wide freeze with nowhere reliably warm left to retreat to, arriving on top of a world that has already lost its coastlines, its power, and half its farmland to everything that came before it. What did a ring like that actually do the last time it hung over Earth? Here the story turns backward on itself, because this is not only a forecast, it might already be history. About 466 million years ago, a large asteroid wandered inside Earth's own Roche limit, the same invisible boundary that would one day tear the moon apart. Earth's gravity shredded it in place, rather than letting it fall as one mass, and the debris settled into a ring circling the planet, a stretch of time so early that dinosaurs would not exist for another 200 million years. A 2024 hypothesis from geologist Andy Tompkins at Monash University argued this actually happened, and the evidence had been sitting in the rock the whole time, waiting to be read correctly. Every impact crater from that period lines up the same way. All 21 confirmed craters from that era sit within 30 degrees of the equator. More than 70% of Earth's oldest, crater-preserving crust sits outside that narrow band, spread across every other latitude on the planet. So an ordinary scatter of asteroid strikes should land mostly outside the belt too, not entirely inside it. That is not chance. Landing on the same face of a three-sided coin 21 times running is not chance either. A ring, shedding debris steadily onto the equator beneath it, orbit after orbit for as long as it lasted, explains a pattern nothing else does, and matching layers of meteorite debris buried in the rock from that same period, the same telltale grains, turning up at sites far apart, back the story up. Not a coincidence. A signature, left in stone, 466 million years old, and only read correctly as of September 2024. The proposal went further, carefully, and not as settled fact. That ring's shadow may have helped trigger the Hernantian icehouse, one of the coldest stretches in the last 500 million years. Tropical sea surfaces measured in the rock, cooled by something close to 8 degrees Celsius by one estimate, enough to turn a warm coastal sea into a cold one, 10 degrees by another, alongside a 100-meter drop in sea level. Roughly a football field stood on its end, drained straight out of the ocean basins. Tonight's own scenario borrowed that same rough figure, 8 degrees, without ever explaining where it came from. It came from here, from a ring Earth may have already worn once. But the case is not closed. A separate study, working from a more refined timescale of the same event, argued the actual debris reaching Earth was too thin, too slight, to have changed the climate at all. So the ring may have cooled the world by 8 or 10 degrees, exactly as the studio's own figure guessed, or it may have hung there quietly for millions of years and cooled nothing, and the icehouse would have arrived on its own regardless. Both readings survive in the same scientific literature, unresolved, published by researchers who looked at the same rock and reached different conclusions about what it proves. That kind of honesty is worth more than a tidy answer would be, and it belongs in the story rather than being smoothed over. One thing the rock record does settle, and it corrects the clock this whole hour has been quietly running on. Debris from a shattered world does not gather itself into an orderly ring within a human lifetime, or even a few of them. It falls and drifts and resettles for millions of years before anything like a stable band exists, not the tens of thousands of years a casual guess might reach for. Whoever is alive when the moon breaks apart will not live to see the sky finish clearing. Neither will their children or theirs. And even once a ring looks stable, do not mistake it for old. Saturn's rings, the ones every telescope points to as some ancient permanent monument, are startlingly young. Likely under 100 million years old, a small fraction of Saturn's own age. The dinosaurs walked under a bare sky. Saturn had no rings yet either, and would not for tens of millions of years after the last of them died out. A ring, once it exists, can look eternal from a distance. It rarely is. A shadow then. Not a strike, not a wave, not a fire. The slowest weapon in the whole scenario, and possibly the only one Earth has already survived, once, long before anyone was here to see it happen or read the rock that recorded it. One question is left standing after all of it, whether any of this could ever really happen at all. That is, in the end, a physics question, not a storytelling one. So it deserves a physics answer. Go back to the picture from the very start of the hour. A cannonball fired so hard the ground curves away beneath it as fast as it drops. So it never lands, it only circles. That is not a trick of language. It is the actual mechanism holding the moon up right now. At 1.22 kilometers a second, it moves sideways fast enough that the curve of its fall matches the curve of the Earth, dropping away beneath it. It perpetually falls, and it perpetually misses. That balance is not fragile. It is not one solar flare or one wrong nudge away from failing. It is stable, in the way a whirlpool is stable. In the way a spinning coin balanced on its edge is stable only because it keeps moving. Take away the motion, and everything changes. Leave the motion alone, and it holds. And the distance itself is not a close call either. The point where Earth's gravity would actually be strong enough to tear the moon apart, the Roche limit from earlier in this hour, sits roughly 20 times closer than the moon's real orbit. The moon would have to fall to a 20th of the distance it currently keeps before that boundary meant anything to it at all. And the motion is not carrying the moon toward us. It never has been. The real moon is receding, not falling. Every year it drifts a little farther out, roughly 3.8 centimeters. The distance tracked for 5 decades by bouncing laser light off mirrors left on the lunar surface, precise to about the width of a fingertip across 250,000 miles. Not a rough estimate, not a model. A direct measurement, repeated thousands of times, from 3 continents, for 50 years running, the same kind of measurement that once confirmed a slipping orbit could never have gone unnoticed either. The countdown this hour has walked, closing distance, rising tides, a moon aimed at Earth, runs in the opposite direction from everything the actual sky is doing above us tonight. So, what would it actually take to reverse that? Not a push, not a nudge. Overcoming the moon's own orbital motion outright. Something on the order of 3.8 times 10 to the 28th joules. For scale, all of humanity, every power plant, every engine, every device on the planet, used about 6.2 times 10 to the 20th joules in 2023. Dislodging the moon would take something like 60 million years of that entire global total, spent all at once. Nothing tracked in Earth's neighborhood carries anywhere near that kind of mass or speed. Every asteroid and comet astronomers currently track, even the largest of them, is a pebble next to that number, its own momentum too small to register against the moon's. Only the close passage of another star or some massive wandering body could supply it, and those encounters are almost unimaginably rare. And even then, they tend to disturb the outer planets over millions of years, not reach down and seize the moon directly. The moon's real future is not a collision. It is a long, slow drift that eventually just stops. The oceans driving that drift are expected to boil away in roughly 1 billion years. And once the water is gone, so is the friction, and so is the outward crawl. Long before then, in something like 6 to 7 billion years, the sun swells into a red giant, reshaping both worlds well ahead of the theoretical point, some 50 billion years off, where Earth and Moon would finally lock face to face forever. That point is never reached. What actually happens to the Moon's orbit after the sun burns down to a white dwarf is one honest question nobody can answer yet. We do not fully understand it. The modeled outcomes range from a quiet ejection into deep space to an eventual fall on timescales of tens of billions of years, so far beyond anything worth losing sleep over that it barely counts as a future at all. It is the one piece of this whole hour that stays genuinely open, not because nobody has looked, but because the physics that far out has never had anything to observe and confirm it against. Even so, it is worth sitting with the 2 ways this hour's imagined version could have ended, because the reasoning matters more than the ending does. One version is fast. The moon crosses the last stretch of sky in hours, and it is over almost before anyone understands what they are looking at. The other is slow. The version this hour actually walked, drowned coastlines first, then the ground itself waking into quakes and eruptions, then a shattered moon widening into a band of debris at the Roche limit, a ring that would look, from a safe distance, something like Saturn's, pale and beautiful, and up close, lethal. Either way, the surface world does not survive it. Neither version was ever the honest forecast. Both were the shape fear takes when it is handed real numbers and asked to run all the way to the end. Nobody knows exactly how long that ring would take to settle. A rough guess puts it at tens of thousands to hundreds of thousands of years. The one real precedent Earth has, a ring it may have actually worn long ago, suggests millions instead. Either way, drifting debris would keep darkening the sky on and off for longer than any single generation could outlast, tipping the climate toward another deep freeze on top of everything already lost. Could anyone live through either version? Somewhere, maybe, in bunkers sealed deep enough underground, stocked and shielded against a sky that no longer means light or clean air. But the surface world above them, its farmland, its coastlines, its satellites, its roads out, would already be gone, and staying alive underground is not the same as the world continuing. A bunker keeps people breathing. It does not bring back a coastline, a growing season, or a way out past a ring of rocks circling overhead. None of it can happen. Not because the danger was invented carelessly. Every mechanism in this hour was real. The inverse cube pull that raises the tides. The same pull that flexes rock and wakes volcanoes. The same pull that would eventually tear a world apart at the Roche limit. That is exactly why the relief lands the way it does. The physics that made every stage of the countdown believable is the same physics that rules the countdown out. The moon is not creeping toward that edge. It is retreating from it a few centimeters every year, and it has kept its distance for 4.5 billion years, far outside any boundary where its own gravity would ever fail to hold it together. So look up at it now for what it actually is. It is a moon that steadies the tilt of this planet, holding the seasons inside a narrow, dependable band instead of letting them tumble. It is a moon that raises and lowers the tides twice a day, the same pull that once helped shape the first life that crawled out of a shrinking shoreline. It is a moon that is quietly leaving, not arriving, drifting outward on a leash of gravity so patient it will not slacken for billions of years. And it is a moon that, for all the ways this hour imagined it turning against us, has never once actually stopped watching over the water and the ground beneath it, whatever it does next. And there is a whole other question waiting in a world where the falling object overhead is red instead of grey. The moon itself is not going anywhere tonight. It is only getting a little farther away, the way it always has, and the way it always will.